placer ver cómo aquí una idea se ha convertido en realidad. Y quería felicitar a todas las personas involucradas, sobre todo Eduardo Artz, por este logro. Y muchas gracias por la invitación. I have been working actually all my life on voltage-gated ion channels, specifically sodium and potassium channels. And I want to tell you today a story about a potassium channel that we've been working on for the last 10 years, which has harbored many surprises for us. And I want to take you through some of the steps, and it will end with something that we never expected, namely that we might have found something that does not have to do with the channel that we originally were working with, but with something that could have a relevance in Parkinson's disease. So the channel that we have been working is a voltage-dependent potassium channel, KV, that's potassium voltage-dependent number 10.1. It's from a Drosophila mutant that's called etheragogo. And you can see here the relative expression of the protein in different human tissue. And you can see that it's practically only expressed in nervous tissue, namely brain, spinal cord. There's a little bit in placenta, but all the other tissues are practically non-existent. So we were very excited. We thought this is a channel that has an important role in brain function. We transfected cells with this channel, and there are many trains coming this time. We transfected cells, and by, again, coincidence, we realized that this channel conveys an advantage for cell proliferation. And in fact, if you inject these cells subcutaneously, these immunodeficient mice develop large necrotic tumors in a very short time, as represented here. This is a control potassium channel, voltage-dependent KV 1.4. This is the tumor weight after 2 weeks, and you can see that the KV 10.1 has drastically increased the tumor mass. And in fact, if you block this channel with different blockers, so this is the tumor volume as a function of time. Here is the control, where we just give them a vehicle. And here we either give them astemisol, which is an antihistaminic that was sold over the counter, was retired from the market, or cyclophosphamide, which is a cytostatica given to patients, that they're about equally effective in reducing tumor volume. We also tested this in some patients. There was a patient that had a form of leukemia, and these are primary cells from this patient cultured that we treated either with nothing, control, or this astemisol, another drug, or a monoclonal antibody that blocks the channel, and you can see that this drastically reduces the cell proliferation. Now, we were still wondering what this channel does in the brain, so we did many different things. We made a knockout, and we looked at the expression in different regions of the brain, and we realized that it's actually expressed in the substantia nigra. Here you can see a labeling in the substantia nigra of tyrosine hydroxylase, which labels dopaminergic neurons, and KV 10.1. And inducing lesion in this region is one of the acute models for Parkinson, which is induced by injecting locally 6-hydroxydopamine, and it caused a loss of dopaminergic cells as expected, but also it reduced the amount of KV 10.1. So during these experiments, there was a postdoc from Brazil that came new, and it was Christmas time, and he had to feed the mice. And he, by mistake, took food that contained doxycycline, which is a drug, antibiotic used for conditional transgene expression. And he didn't know this. He was just using it. This food is colored. And he then noticed that, surprisingly, this food protected them from the 6-hydroxydopamine damage. So the Parkinson is due to death of dopaminergic neurons, as represented here and expanded in this figure. And yesterday, Christian Griesinger showed a movie of a Parkinson patient, how it affects the motor behavior. And as mentioned, I think by Tom Jobin, it's a Bermuda Triangle of Parkinson's, because depending on who you ask, different people think it's either oxidative stress induced by reactive oxygen species. Luis Barbietto showed us also that activated astrocytes are involved. Christian Griesinger showed data on alpha-synuclein. Other people think that metalloproteinases are involved. So depending on many aspects, it's a complicated disease, and what the real causes are not quite understood. There is a link with neuroinflammation in Parkinson's disease, and it's been discussed as a target for neuroprotection. You cannot see it here in detail, but the astrocytes get activated, and it is kind of a feedback loop where the damage always increases more and more. The model, the acute model of 6-hydroxydopamine is presented here, where these mice have been injected in the substantia nigra with this neurotoxic substance unilaterally, and it produces a rotating behavior that you can see here. So these mice turn around in circles. Some stop for some while, but then they continue, and they always turn around in one direction depending on where you place the lesion. Now, these are mice that had received normal food. However, the ones that had been fed with doxycycline showed a totally different behavior, and surprisingly, they were practically unaffected by this lesion. The amount of food given is the one that normally is given to turn on the transgene. It's also within the range of what patients take in doxycycline, which is an antibiotic that is taken for many different indications, has many different effects. It's also taken, for instance, for malaria. And a quantification of this rotational behavior is shown in the next slide. Many of my slides will have the same format. This is the control when the mice have been injected with saline in the corresponding unilateral lesion. Normal food or food with doxycycline. And this is the number of turns per minute, and you can see there's hardly any difference. That's a control. Now this is the number of turns after inducing the lesion. With normal food, you can see it increases drastically. However, doxycycline food or doxycycline injection subcutaneously greatly reduces this turning behavior. So we went to see how the dopaminergic neurons behave, and this is now labeled substantia nigra without doxycycline plus doxycycline as a control. You can see that there is damage, and this is this is no damage, and you can see the damage induced when you do the lesion and give them normal food. However, the decrease in tyrosine hydroxylase and dopaminergic neurons is much lower, either again with the doxycycline containing food or injection. And if you look at GFAP, which is a marker for adult astrocytes, gliofibrillar acidic protein, you can see a reduction. Strange enough, there is an increase, so green is GFAP, there is an increase on both sides, and there is a reduction in tyrosine hydroxylase here in this region. However, these are the mice treated with doxycycline, and you can see that there is much less adult astrocytes in both sides. Again, looking in more detail, here is again tyrosine hydroxylase and astrocytes. Shown here, normal control. Here is the ones, again, treated with doxycycline. And you can see here a clear difference. These are the ones treated with doxycycline, how it protects from the effect of the lesion, which is shown here. looking into more detail in here, you can see here again the loss of tyrosine hydroxylase on the lesion side and the invasion by the astrocytes in this region. The contralateral side, there is no reduction in tyrosine hydroxylase, but still invasion of astrocytes. Okay, so somehow the doxycycline protects, and this quantification of this is again shown here. This is a band for anti-tyrosine hydroxylase and anti-GFAP, and again you can see here the lanes that are given doxycycline are different from the ones from the pure lesion in terms of tyrosine hydroxylase and GFAP. Now, one thing that might indicate an effect of microglia is to use a marker, and here is a MAC1 marker for microglia, and again this is the control in saline with and without doxycycline. Without doxycycline normal food, you can see here the activation of microglia in the region, and there is still activation, but much less in the mice that were treated either with food or with injection. So this effects of doxycycline seem that they block the 6-hydroxydopamine neurotoxicity in vivo by reducing glia and microglia. The doxycycline may be ineffective in preventing or slowing the progression of Parkinson's and other neurodegenerative diseases. We looked in the literature, and there have been clinical trials using other antibiotics, tetracycline mainly. It was known that they protect somehow, and the ideas that were forwarded is that it affects the metalloproteinases. We checked for that. I'm not showing the data. Doxycycline has no effect on the metalloproteinase activity with or without treatment. We still don't know what the cause is. I'm presenting this just to show you an interesting aspect of doing research, that if you look carefully, sometimes things happen that are unexpected. And it's also a warning, because many people use doxycycline as a conditional transgene expression modulator, and one has to consider that this has other secondary effects. I wanted to be brief, just to present one aspect of the work. We're very excited about it. We still don't know, as I said, how this comes about. And there seem to be, I haven't heard what the clinical trials were stopped, the ones with tetracycline. I wanted to say that the dose is a dose that is given to patients normally. The question is still about the timing. When do you start the doxycycline treatment? The cases that I was showing, the treatment started before inducing the lesion, and obviously you don't want to take doxycycline as a preventive medication against Parkinson's. We're doing experiments where we're doing the lesion and afterwards treating with doxycycline, and I can say that the preliminary results show that there is a protective effect still there, so it could be something that can be used. A word of caution is that the 6-hydroxydopamine is an acute model of Parkinson's, is not the way the disease develops, which develops slowly over many years, so these things are not comparable. Still, I think it's an interesting observation. This work could not have been done without the collaboration of many people, Elaine Delbel and Marcio Lazzarini from Brazil, where we have an intense collaboration, Sabine Martin, Luis Pardo, who has been with me over many, many years, Fernanda Ramos, also from Brazil, Miso, Frank Kirchhoff, José Ufartes from Spain. And there have been invaluable technical input from technicians from different laboratories, without whom this work would have been impossible. Thank you very much.
Thank you for your talk. We have time for questions.
Sorry? No, but Actually, yes, that's a good idea. Yeah.
Yes.
Herr Stümer, have you done a gene expression profiling and looked for P450s, tyrosine hydroxylase, topohydroxylase? I would speculate that's where you are.
Yes. We did it, and we had many hits that need confirmation. Like, you know, you always get hits and have to look at in detail how they work. We're in the process of doing that.
Have you looked at pro-inflammatory markers expressed by microglia?
Yeah, the
Let's say-
MAC1.
Let's say cytokines.
No, it's known that cytokines are elevated in Parkinson's. We have not looked for that. We have just used the MAC1 indicator for activated microglia.
Well, Walter, this is very exciting work. Have you looked at mitochondrial morphology and function?
Yes, mitochondrial. It's also thought that energy metabolism and mitochondrial damages are at the basis of Parkinson's. We've looked with normal means up to now. We have to look into more detail. And as I really said, these results are from, you know, the feeding. This was done this Christmas, so we're still at the very beginning. From what we can say up to now, we have not looked in detail. There are no gross no big changes in mitochondrial morphology.
How about a number? I mean, one of the main expressions of the situation that arises under oxidative stress is that you have an interruption of mitophagy, or at least a perturbation of mitophagy, so that the number of mitochondria.
The number of mitochondria decreases. We have not looked at that, no.
More questions? Okay, thank you, doctor. We are passing